Hello, how are you? My name is Mohindo Mubarak, and I'm with my colleague Joshua Mhanga. I'm going to present the progress of our work, which is federated few short continuous learning for medical image processing with federated feature augmentation. And our keywords are there displayed on screen. So we're going to our program. We have organized it into this way. We shall begin with the introduction, following our related work. Following the related works and problem statement of our work and the research questions and objectives, research contributions that we shall make, methodology and the system architecture. Then the data set description. We shall describe what we have. We're going to use the data set and as well as the results and experimental simulation results and conclusions of this anticipated and limitation of our work, and then plan and feature plan and references and also acknowledgements. So that's how we're going to present today. So let's go straight into today's business. So the motivation for this research, the traditional centralized medical image analysis it violates the potential privacy and demand extensive. The current way how things are being done is the common current way that how things are being done is that when there is a need of data set, the image have to leave the owner's device or the agent's device and go to the server for it to be processed. So that can bring the breaking of what? Of privacy. And the federated learning, FL, preserves privacy by training on distributed nodes. So our work wants to focus on training the models on distributed computers without the data leaving the original device. And then few learning addresses the limited annotation scenario, and continuous learning adopts the models over time as more data comes in. So these are going to help us to solve the problem of privacy in a way that the image we shall be training them on different nodes, and then we send them to the server, to the centralized server. That we send the application model to the centralized server that will be updating in one place without using the physical images from the device, and the image and the model continuously learning. So to develop an integrated artificial intelligence framework, we shall need to use FL, few shots, and continuous learning. Continuous plus federated continuous learning plus and federated feature augmentation that can diagnose malaria quickly and adapt to new data without centralizing patients' records. And we are doing this not specifically for malaria main, but we're using malaria as a use case. However, our architecture can be benchmarked on to deploy, even to implement other kind of use case, not limited to malaria. So this is our architecture of the program, of our framework that we want to come up with. We shall have a model on the server, the central model that shall train first, and then we shall deploy optimized model on different client computers, where they'll be training on different servers on the different agents. And then after training, they'll be sending this data to the centralized model, and then the model will be getting the average of the work and then update itself and then distribute that model to other people who may need to use it. So shall literally have two categories of people: those who will be using for training, the clinical medicines or the agent that you have for training, and then those who will be using this continuously learning or continuously improving model for their purpose or for the use of purpose. So that is how we are designing this work or this framework. So the recent works in this, we researched and found out that Mark Mahan 2017, they introduced federated learning to train machine learning models across decentralized data while preserving the privacy. And also recent advancements in federated learning in computer vision tasks by Sanaj in 2023. 2023 or in 2023, yeah. And then we have few shot learning by Finn et al., which is the work that was produced 2017. And then in continuous learning, we have Parisi in 2019. He reviewed the techniques of incrementally learning from the new data. And this helps us to accurately, to the accuracy of evolving the data distribution. And then lastly, we have the medical imaging for malaria. And previous work was utilize the deep CNN. However, the data privacy and distribution remain unresolved even in this case. And you can search about it. So our approach combines federated learning, feature, and continuous learning with federated feature implementation to address this issue of what? Of privacy. And our main computation challenges, our main computation challenge is balancing the privacy, keeping the potential data on the local device of a user with accuracy, with accurate classification of malaria-infected cells, and handling the limited label data in each clinical site, which were to, so since this data on a certain clinic will be little, so shall use the technique of few-shot learning scenario. And then ensuring the model continuously improve with incoming data from models themselves, not images. So why it matters, centralized data solution compromises the privacy, or it is infeasible, or they are infeasible in low resource settings, where you have maybe a limited computer or you have a limited storage, and you cannot store all these images on one disk. Okay, let's say that you can store them, but processing them on one computer. But here we can have like maybe, let's say, 100 phones that can process data on their respective device, and this data come with a model on the central server with a model that has already been trained. So that saves a lot of space and resource. And malaria evolves. New strains or varying patient demographics require continuous learning. My colleague will start from here. Yaranga.
Thank you very much, Linda. I will start from the research questions and objective. Our first research question is, how can federated learning be adapted to ensure privacy preserving malaria diagnosis across distributed hospitals? Second is, what strategies can enable official learning to overcome the scarcity of labeled data for the new local clinic? The third question is, how does continuous learning maintain model performance as the new data arrives over time? Then, which future augmentation techniques improves diagnostic accuracy in a federated environment? So as you're aware, federated learning involves you have a central server, then you have a local nodes. This nodes represents a clinic. So the clinics will train the model locally and only sends the model updates to to the central server without sending the data. So that will help to preserve privacy. So you also do realize that most of the clinics do not have sufficient data to train an accurate model. So we are utilizing few shots learning to train limited data while improving accuracy. And then continuous learning, normal, we have new disease, say like malaria, normally presents itself with different symptoms. So our approach will ensure that as new data comes in, these updates will be sent to the central server. So objective at most, we are to design a privacy preserving federated learning framework for a malaria image analysis. Two, we shall also integrate few short learning methods that allows rapid local adaptation with minimal labeled samples. Then shall also implement continuous learning for real-time model update without loss of the previously acquired knowledge. So to evaluate the proposed system diagnostic accuracy on real data and on real world distributed malaria datasets. Can you move to the next slide? So the research contribution, we shall have a novel federated learning architecture. This architecture will integrate few shots learning with continuous learning and future augmentation. The major emphasis is we have to ensure that the data, the local clinics maintain their data at any point does not leave the local device. So we only ensure that the local clinics will only send the updates, the model updates to the server. So next we have incremental adaptation demonstrating how continuous learning ensures system remains up to date with evolving clinical data. Then empirical validation, deploying the solution on the 6 layer dataset and showing the improved detection accuracy. Move to the next slide. Hello.
Yes, I've moved the next slide. Methodology.
Move to the next. Okay, the methodology is the system overview. A central federated server coordinates a model aggregation, multiple clinics, multiple clients clinics, train model locally, periodic weights updates, and exchange instead of raw data. So what will happen in our methodology? We shall have a central server. So the central server starts we start a central server. So the central server begins by searching the best parameters. Once it gets the best parameters, it uses those best parameters obtained to train the best model. So once it's done training the best model, which becomes our global model. So once you start the clinics, these clinics will use the best parameters and the weights from the server. So they use those as their starting point for training their local model. So once they receive these updates, the local clinics they will train their independent models. Once they are done training, those updates are sent to the server. depending on the rounds. If there are 10 rounds, it means that each clinics will train their data like 10 times while sending the updates. So the server receives the updates from each of the clinics, then does the aggregations. After doing the aggregation and the final round, the final global model is sent to the respective participating clients. So the core components, we have few-shots learning model, which is basically for local adaptation using minimal data. We've got federated feature augmentations. So this helps in aggregating features to enhance classification robustness, then continuous learning mechanism ensures that once the new updates come in, these are sent to the model without starting from the afresh. So the workflow is server broadcasts global model to each nodes, local updates, each node trains on a local data set, that is the few-shots, and then the server aggregates updates. Continuous learning, a global model is refined over time as the new data arrives. Let's go to the next. So our data sets consist of the sick blood smear. They are labeled blood smears indicating whether it is a parasite blood smear or it is an infected cell. Processing. So the first step for processing, we are resizing the images to 128 by 128. This is to enable that we have a uniform size across through all the images. If we don't have a uniform size, then the model may either overfit or it may tend to follow the same pattern, causing overfitting. Then we have also to normalize cells. So we divide each pixels by 255 values, such that we obtain a value between 0 and 1. This also helps to avoid the overfitting in the model. Then data augmentations. This involves the rotation, flipping, light brightness. So this is done to enhance the features of the images. Then the sample distribution, we have around 12,481 parasites images. Then the same number for infected, meaning the data is balanced. So this is divided into training, validation, and then the testing sets. Then the database, we have the Clash contrast presentation. So, and Clash contrast presentation.
Yes, Joshua. Joshua.
Yes, please. Um, then this table here represent to you the data set statistics. We have the total sample size, which is 200 and that is 24,000 962, and of those, we've got the training sample, we've got 9,985. Then that is for parasite cells. Then for uninfected, we've got 9,984, a difference of 1. So meaning that our data set is balanced. So this that number represents the number of the test sample. Then this is the total number of samples. So under results, we have a result for the CNN model that is over 10 rounds. This means that the participating clients went through the 10 rounds. So in each round, you have accuracy value, the precision, recall, F1 score, and specificity. And then we also have a performance for this one was for exception model. And through, if you look at the table for CNN model, it showed a great improvement from the first round to the last round, achieving a precision of 97%, which means that this model can accurately distinguish between malaria patient and a client who's not affected by malaria parasites. So the same applies to when you come to the exception model. It also showed a steady progress across through the precision. So you see, started with 91, and later there was a decline, but overall the precision is a bit fair enough. Though here the CNN model performed extremely well. So let's go to we see our proposed model performed. Okay. Key takeaway conclusion: the federated approach successfully maintains patient's privacy. E-shots learning effectively handle limited annotations in the distributed setting. Continuous learning sustains performance over time, which is crucial in evolving critical conditions. Impact, then the potential to revolutionize malaria screening in low resource health care facilities. It also offers a scalable privacy first solution for other medical imaging tasks as well. Then anticipated limitation and counter action plans. One limitation, competition constraints at some clinics. Edge devices may struggle with heavy modules. So we have non-ID data distribution across sites. This could also affect convergence of the model. And then communication overheads. If the networks are poor, most especially within the rural areas, then the generalizability to other diseases, imaging modalities require further validations. Then the countermeasures shall have a lightweight models, variant or quantizations for edge devices, advanced aggregation techniques such as FedProx, which will handle the non-ID data. Then we shall also use the adaptive communication schedule to reduce bandwidth usage. Shall also do a progressive fine-tuning for other medical domains. So those are the references from where we obtained our work. So acknowledgement, we gratefully acknowledge Makerere University and the local health care partners for their support and access to facilities. Special thanks goes to Welwangom Marvin, the machine learning engineers, for his constant guidance and support that he has provided to us throughout this. We thank you. That was our presentation.